Hey physics students, time for another online lab. This week's lab we're going to be talking about reflection and refraction. We're going to start with reflection. You can follow along in your lab manual, Experiment 8, Reflection and Refraction. We're going to be following this procedure, but of course doing it online. So starting with reflection, we're talking about something like a mirror, right? So imagine here you've got this little mirror. Some object is in front of the mirror, light comes in and bounces off the mirror. We're going to be talking about a single ray of light here. Of course, we think of light as waves, and of course we think of multiple rays, but just for simplicity we have a single ray of light, and we want to look at what happens as it bounces off of this mirror. So first of all, we have to always think about everything in terms of a normal. Alright, and it's very hard to draw a dotted line. So in terms of a normal, and by a normal I mean the line perpendicular to the surface of the mirror. Every time we talk about angles with reflection and refraction, they're always relative to the normal. So the first thing we want to talk about is how the incident angle, okay, theta little I, is equal to the reflected angle, theta little r. This is the law of reflection. Okay, the law of reflection just says that the angle incident is equal to the angle reflected from the normal, right? Don't forget that, from the normal. One other piece here that you're not going to get to explore so much, unfortunately, in your online simulation is when we're thinking about reflection, you need to think about where the object is. So this was our object, and where the image is. The image is directly opposite the object on the other side of the mirror, and the distance, I like using all these different colors, is the same. That object is directly behind the mirror at the same distance away, even though my drawing is not that great. So P is the object distance, Q is the image distance, and you experience this every day when you look in the mirror. You look to be directly behind the mirror. Okay, so that's one thing to remember about reflection. We are actually now going to move on to refraction. So refraction, and we're going to be looking at the law of refraction just like we looked at the law of reflection. Refraction is when light is bent as it passes from one medium to another medium. Of course, here we are always going to think about what happens relative to the normal. Okay, there's my normal, as best as I can do it. We are going to have light come in, and it's going to come in at an angle of incidence. This time we're going to call it theta 1. And what happens when it passes into a second material, the path may change. So let's assume that we're starting out in air or a vacuum, and we're moving into a material like glass or water or plastic or something like that. What's going to happen? Well, that light is going to get bent. In this case, it's going to bend toward the normal. And by toward the normal, I mean that the angle here is going to be smaller than the incident angle. We're going to call this one theta 2. And Snell's law, or the law of refraction, tells us that these angles are related. So Snell's law, or the law of refraction, says that these angles are related, and they're related by the material properties. So N1 is the index of refraction times the sine of that incident angle, theta 1, is equal to N2 times the sine of theta 2. Okay, so I've introduced N. Let's talk about what that is. So N1 is the index of refraction for air, in our case, or the first material. So N is the index of refraction. For air, the index of refraction, N equals 1. We have the second material, though, here. We have N2 for our glass. Now, what can we know about N2, or what can we say about it? Well, there's a couple of things. One, we know it's related to N1 and these angles by Snell's law that we just went over. But sort of thinking about it more conceptually, another way to define the index of refraction is to relate it to the speed of light. And the speed of light in the material, such as glass or plastic. So the index of refraction is the ratio of the speed of light in vacuum. So this is vacuum. So we use the regular old C, speed of light, vacuum. Sorry, that's a terrible vacuum. Versus the speed of light, it's not letting me draw, the speed of light in the material, whatever that material is. So I want you to notice here that N of air, we said was 1, right? So N of a vacuum, or air, equals 1 because the speed of light doesn't change. But in glass or water or things like that, V is less than C. That light actually slows down, which is why we see a change in the angle here. So another way to think about this, sort of going back up to our angles, is the light slows down here as it comes into the glass in this case. Glass has an N that is greater than air, so N2 is greater than 1, and so that tells us that the velocity is less than C. And that also tells us that this angle, theta 2, is less than theta 1. We call this bending toward the normal. So it was farther away from the normal, now it's toward the normal. And that's what you get when you pass into a greater N. And you shall see that in the simulations today. Okay. All right, next step is to talk about a prism. So instead of just having a straight slab interface, what if we have a prism interface and light gets refracted inside of the prism? That's going to be the last thing that we are going to investigate. Again, let's think about those normals. Try drawing my normal here, and you can think of the normal actually passing inside of this prism as well. So we've got our normal. We're going to have light coming in at some incident angle. Right, this time I'm going to call the incident angle theta sub capital I. I want to have different notations for the incident angles for each of these cases just to keep them straight. It comes in at that angle, right, from the normal, not from the surface, from the normal. You're going to use a protractor, and you always want to measure from the normal. Then what's going to happen to this light? Well, here's my normal, right? If it's going into glass, here's N of air is 1. Inside it's 1.5-ish. Okay, and then outside it's 1. It's going to bend toward the normal. Okay, so here it is. That means that as it's passing, this angle as it comes through is going to be smaller. This interior angle, it bends towards the normal. Then what happens out here? Let's draw another normal, and it's normal to the surface. Let's pass it inside. So what happens here? We reach another surface. This time we go from a bigger N to a smaller N. The process reverses, and we bend away from the normal. So this exit angle right here is actually going to be bigger than when it encountered the normal here inside the glass. So bends toward the normal, bends away from the normal as it exits. Cool? Okay, but we actually want to do something slightly different here. We want to measure what we call the angle of deviation. So the angle of deviation says, well, I had light coming in at this angle. If it didn't pass through the prism, it would have just kept right on going, right? And so the angle of deviation is how much did it change? It's the difference between its original coming in and its exit. But it's not the same as this exit angle, right? It's a whole different angle. It's this angle D, the angle of deviation. So angle of deviation. Why is that important? Well, it turns out that you can relate the angle of deviation to n. You can figure out, say you don't have a glass prism, you have a plastic one or something, you can figure out the index of refraction if you know the minimum angle of deviation. So the equation goes like this, that you take the sine of A plus dm divided by 2 over the sine of A over 2. Okay, so hopefully you're asking yourself, what is A and what is dm? A is the angle of the prism. So A, oh, come on pen, is the prism angle. If you have an equilateral, it's 60 degrees, right? Remember your geometry. And dm is the minimum angle of deviation. So it's the minimum d. And you're going to do several measurements with different incident angles, theta I, and see how that affects d until you find one with a very small d, and that'll be your minimum d, the smallest one that you find. Okay, so let's quickly switch over to what the simulation looks like. This will be pretty straightforward, I think, you guys. So you'll pick this bending light off of the FET light and radiation. You'll come here. It'll look like this, if my computer can keep up with me today. Okay, when you pull up the simulation, you'll first have a choice of intro, prisms, or more tools. Pick the intro and you'll see something like this. You have a little laser here, you turn it on, and you can see it refracts through this material and it reflects off of this material. You can switch what the material is. You can switch, just pick different index of refraction and see how that changes things. And finally, you have a protractor tool here that you're going to be using to measure the various angles. Be careful that you always are measuring from the normal. So drag that thing, line it up with the normal at 0, and then you can measure the angles. You can move this little laser guy. You'll have fun playing with that. One note on the protractor, when you get to the prisms, here's your second prisms, you're going to be doing an equilateral triangle. Boop. The protractor is a little bit trickier on this one. You will want to drag it around by the middle bar, and then you can rotate it like this. It's a little trickier because you're going to want to, again, line it up with the normal. It'll show you the normal. You'll want to drag it over here and put it so that sometimes you have it aligned with the surface of the printer. That crossbar is aligned. The zeros lined up with the normal, so you can read the angle there. And then you'll have to rotate it around to read the angle of the deviation, because the deviation angle is going to be the difference between where you started. So I like to do it with 0 here. It starts out at 0. That means it should continue at 0. Look on this other side, 0. And then you can read the angle here. Okay, so have fun with that. Follow the instructions, take your screenshots, and submit everything, including your calculations. Follow those in the lab manual. See you soon.